on air where we bring you the tech content that you crave. I'm AM Grabelny, solution architect here at AWS and one of the AWS On Air hosts. I'm joined by a couple of friends here. Jillian, tell us about yourself. Who are you?
Hey, my name is Jillian, and I'm a startup solutions architect at AWS.
And Michael, too. Michael's our guest. Michael, you're joining us here from Neural Magic. Tell us about yourself.
Yeah, hi, my name is Michael. I'm a product engineering lead at Neural Magic, and I'm here to tell you about all the exciting developments we have today.
Okay.
Yeah, Michael, tell us, what is Neural Magic?
Right, so Neural Magic is all about tackling the problem of optimizing our models for machine learning. As you know, machine learning models have been a great advent. You can use them for a wide variety of tasks, from computer vision to natural language processing to even generating whatever weird image you think you can come up with. And as these models grow larger and larger and get more and more accurate, of course, how we've generally thought about scaling and running them is just by throwing more and more hardware at it. And especially throwing more specialized hardware that just does machine learning training or inference. So our sort of story focuses more on, instead of taking this brute force method of changing and designing our hardware in different ways, we've already made really general purpose, wonderful CPUs that are commodity hardware running everywhere, all over every cloud, all over every laptop or phone you own. Why not just make better algorithms that execute these models more efficiently with more heuristics and sort of flip this problem on its head? And so Neural Magic started with this sort of fundamental question of studying the brain and studying connectomics by our founders from an MIT lab. They found, and we know that brains generally are kind of having a cell phone amount of compute compared to like a petabyte of memory, all sparsely connected up in your head. And this is generally not what we've really done. You look at like a server or something, you're talking about petabytes and or petaflops, and starting to get into exaflops of compute, and then you're just talking about a couple terabytes of memory here and there. So it's orders of magnitude less memory compared to orders of magnitude more compute. And the brain is the complete opposite of that. And so what we decided to focus in is exploring what you can do when you start making neural networks have this sparse architecture.
Hey, Michael, you mentioned cell phones, and that's the power of human beings' brains. Personally, I don't think mine is quite up to like a modern phone. I think I'm more of like a Nokia. But look, and I didn't want to share this with you earlier. I was afraid you're going to judge me, but this is a judgment-free zone, I hope, Michael. I am not a machine learning expert, but I am a solution architect. And so one thing I do understand is optimization, and I definitely understand cost optimization. And it sounds like, from what you've been telling us so far about Neural Magic, these are two areas that Neural Magic focuses on, right? So, I went and looked at your website, see the word sparse everywhere, right? So why are you focused so much on this sparsity? What is it? And how does it actually tie into optimizing ML workloads?
Yeah, I can absolutely answer that. So sparsity has been a concept for decades, larger than Neural Magic has been around. The research has absolutely been there. People have been figuring out ways to train these dense and large models and pick apart and prune away all the parameters that aren't necessarily important, and optimizing these models either for extra space on disk or whatever you can think of. And this totally fits into the larger scope of optimizing your models. Most people know this by quantization. This is a very common flow of, okay, instead of representing each parameter as a full floating point, large precision number, now you can start to cut things down by represent them as a small, maybe just 8-bit integer, like a Boolean value or something very compressed in memory, you can, just cut everything down by a quarter in terms of all the memory you need. And there's even hardware to have support for doing operations in this low precision format. And sparsity is just another optimization on top of that. You can think of quantization as sort of removing all the precision you need for all those values and just keeping the magnitude of the values. And sparsity just makes it so now we just need less parameters. Right, quantization is reducing the precision of all of your parameters, and sparsity is taking advantage of you just have too many parameters. In removing a lot of these parameters, you can now have these large matrices of parameters that are sparse. You can compress these just like you would a zip file or anything you'd like to, or an image you'd like to compress to send your parents. And this is really easy to do. The hard thing is to get a speed up at inference time, taking advantage of all these sparse connections, all these sparse parameters. And here is the magic that neural magic really adds in terms of pushing forward the research and how sparse can we get these networks. We've proven you can take benchmark state-of-the-art models like BERT or just transformers in general, or YOLO object detection models, and get them to 80%, 90% sparsity while maintaining 99% of the full dense model's accuracy. And this is really great research. But it doesn't matter that much if people can't really get a speed up, get that additional optimization on top of other forms of optimization like quantization. And so what neural magic brings is an inference engine designed for CPUs to take advantage of that flexibility and the unique topologies of CPUs, having large amounts of really, really fast cache for each core, only having a small number of cores. And you can really start to flex this sort of brain arrangement we talked about earlier, right? This is the wonder of CPUs. GPUs sort of have like all this dense compute packed in together, but then maybe just 16 gigabytes of memory packed in against that. CPUs have these terabytes of memory they can access and these large caches, and so they work really well for these sparse computations to really punch above their weight once you've taken the time to design algorithms for them.
Yeah, Michael, I want to go back to a point you made earlier, because a lot of people probably heard this, are like, wait, hold on, time out. Because I work with so many startups where when they want to improve the performance, they just increase the hardware, or they just add more GPUs. So what you're saying with neural magic is you can use CPUs and you don't necessarily have to just keep increasing the hardware to get performance optimization benefits. It sounds like with neural magic, you don't have to keep just increasing the instance size in order to really start getting performance benefits. And you don't necessarily have to use GPUs, at least specifically for NLP and computer vision problems. When I work with startups, that they usually just want more GPUs and just to keep increasing the instance size.
Yeah, absolutely. And this is what we find, ourselves. We do most of our testing, development, benchmarking. When we're moving to the cloud, we do it on AWS. And this is because most of our users are using this kind of hardware. They're using AWS. They're using all of these various integrations or special environments. Okay, all right.
Yeah, sorry about that.
Okay. Yeah. Right. So we find most people are using these kind of environments that AWS provides, like Lambda or Sagemaker or EC2 instances. And a lot of people have these instances reserved for a long amount of time, or they have, all of these CPU instances just available because every instance comes with a CPU. And so, absolutely, we find this to be true, that people usually, they want better models over time. They want them to be more accurate. They want to drive their more value for the customers, but they don't want their costs to increase over time. And so this is where it really makes sense to just make the software better on the same hardware that you're running on. And so we work really hard to squeeze that value out of those CPUs that you have on AWS, all the way from your burstable, quick firing T3 or Lambda instances, all the way up to your large HPC class C6i, compute optimized instances running on AMD or Intel. And we're even working on ARM support for our deep sparse inference engine in the near future. Very much looking to be on Graviton and getting a lot of use out of that.
Very nice, very nice. I heard, someone told me, Michael, that you have a demo for us. You're going to actually show us neural magic working. Is that true?
Yeah, absolutely.
Okay, I'm glad I wasn't lied to. I'm very excited for this. I'll pull up your screen.
Sure. Yeah, got it open.
Take it away.
Yeah. So, right. Yeah. So, want to lay out just how you can find us and how you can see us. All of our work is on GitHub. So all of our machine learning tools, this is SparseML, our libraries for sparsification, SparseZoo, where we publish all of our sparse optimized models and how to replicate them, and Deep Sparse, our inference engine delivering GPU class performance on sparsified models on CPUs, is all available on GitHub and PyPy. It's all free to use in a non-commercial setting. And we're excited for you to get started with it. So I wanted to show you a demo in our Deep Sparse repo. So clicking in here, you can look all around it. So we actually have a Sagemaker demo here. And we have a little README here of how you get set up. Obviously you want to set up your AWS CLI, make sure your roles are all good. So work with Sagemaker, get Docker and Boto 3 installed. And we sort of take you through a natural language processing question answering example here. And I just sort of broke that out into a demo for y'all. And we'll get to the question eventually. Hopefully I haven't spoiled it already of who is Batman. Side note, the context is Mark is Batman. So just to show you where you can find our optimized model. So this is SparseZoo, as I mentioned before. This is where you can find a whole list of models over different domains, like natural language processing, question answering, or text classification, or we can even take you into computer vision, image classification, or object detection. And here we have a list of, BERT models of where you can see for each one, you have different accuracy metrics, speed metrics, and size metrics that vary as you get to different sparsities and levels of quantization. It's all really exciting, fun to look through. You can see the models you've heard about in blogs. And
Michael, this might be a very simple question, and I apologize in advance if it is. When it says pruned, is that in reference to what you were talking about earlier with the parameterization being reduced? Is that what pruned means in this case?
Yeah, exactly. Prune just means it's a sparse model, specifically unstructured sparse. So it means we're totally keeping all of the dimensions and sizes of the large weight matrices the same, and we're just starting to pick out little pieces of them, set them to 0. They don't matter as part of the calculation. You can just skip them or compress them out.
The way that I've been thinking about it, and maybe correct me if I'm wrong, it's kind of like going in and optimizing your database in a way, right? Like if you have a database column that is like a SQL style column that is set to like a float, and you're not fully utilizing that across the data, like changing it to an int value instead starts saving you space within the database and the hardware that the database requires.
Right.
Kind of similar?
Yeah, so I mean, you just kind of described quantization, turning it from a float to an integer, and pruning goes even further than that, right? It's seeing that there's just rows that I would never use or I don't care about. They're like bad data. They don't actually feed any answer I'm interested in. So you could just drop those rows, just get them out of your database. Then all of your searches become faster, right?
Very cool.
Yeah.
So right, the model we specifically want to talk about today is the Stilbert on the Squad data set. This is a question answering data set, really common in research and for benchmarking. And so you can see we have a base model, a pruned 90% model, and a pruned 80% model with quantization. And you can sort of see their accuracy compared with each other. You can see the sizes start to get smaller and smaller, almost an order of magnitude smaller once you get to a sparse quantized model, which we find really exciting. We have some model cards that once you click into, this is the base model of Distilbert. Here is our 80% sparse quantized model. And you can learn about how these models were made and get all the files, the Onyx files, the PyTorch weights, any sort of tokenizer JSONs or recipes of how we made it. All this you can find in here, free to enjoy. And so I have a little notebook here, tying back into that Sparsification, deep sparse Sagemaker integration, just showing you you can use the example like this, just saying we want to create an instance over in US East 1. We want to use a C5 2x large instance, and sort of all of our other commands for pushing up the right Docker image and things like that. And feeding in our role ARN so we know where to run it. So I've already taken the liberty of setting up the endpoint for you all, so you don't have to wait for that to spin up. And we can go ahead and use that endpoint and send off a range of requests, so we can go and benchmark the performance. So it'll take a little bit. I probably should have done a little bit less than 1,000. But just to make sure we get a clean signal for our final measurement. Yeah, well, we can wait a little bit.
Yeah. Michael, I have a question. I know we're seeing this right now in SageMaker, but there's probably a lot of people who'd be wondering if they could run this on EC2 or run this on container. So is Neural Magic agnostic of any of those environments?
Right, absolutely. And we can show that for you right here, in that you can just run it on a normal system you have anywhere. It's just a PyPy package that's easy to install and runs anywhere that you'd like to try it. So EC2, you can use this anywhere in Lambda. You can run it on your local machine.
Yeah, I was going to ask, do you see developers and machine learning engineers just running it locally and before they move to, a shared environment or something?
Yeah, absolutely. People want to try it on their local machines. And yeah, currently we require you run in sort of a Linux environment. So if you're on Mac or Windows, that means trying out a virtual machine. But absolutely, we have benchmarks and reproducible flows. You can find on our website and figure out how to run with us. Yeah, maybe I should speed this up a little bit. There we go.
So this is a SageMaker hosted endpoint that you're currently spinning up right now?
Right. Yeah. So yeah. So it's running on SageMaker, and we're finding the endpoint and hitting it with our question, right? Who is Batman? Mark is Batman, and it comes back with the answer that Mark is in fact Batman. And this is just a simple answer, and it's pretty it's pretty certain about this, and so we can do a similar benchmark using the Hugging Face SageMaker integration, using a similar Distilbert squad model on question answering, and on a similar C5 2x large instance. And we can run this and start to see the performance of the Hugging Face model against our optimized Neural Magic model. Now we can probably skip from this, and I can show you the CloudWatch results.
Yeah, let's see.
Yeah. So right, if you go into CloudWatch and you go into your metrics, you can start to look at these different SageMaker instances you've set up. And here we've chosen to look at the model latency for each of these endpoints. And here you can see in the deep sparse demo latency, we're down to just
That's
40,
significant.
Yeah,
42 milliseconds per inference. Each of those, tens of inferences. And the Hugging Face instance with an unoptimized model is doing 350. So we're talking over 7x improvement at just batch size 1 of just running in a more optimized model and running it on our runtime, which is optimized for these CPUs to get you the most price performance for your application.
It sounds like maybe to put this in very, very reduced terms, I'm sparsifying how I'm about to describe neural magic, but
Yeah.
it sounds like maybe your mantra is waste not, want not, right? Like this is very much a, let's take this. I think I heard you describe it earlier as a software approach instead of an infrastructure approach necessarily. Like to Jillian's question earlier too, we can keep growing the GPU size, the instance size, etc. Or we can tackle this from optimizations at the model level. So just kind of a summary, like as I'm thinking through and seeing all of these wonderful demos that you've been showing us, Michael. Is that a fair summation, you'd say, about neural magic?
Yeah, absolutely. I think you've got it on the dot. Oh, I broke that.
And if I noticed correctly, just from looking at your code, it looks as though it's pretty much, if not the same, or maybe not much more of a difference in the amount of code that's required to actually use neural magic compared to not. So like, it's kind of like a win-win, like overall,
Yeah.
right?
Yeah. Especially in terms of what it takes to get started with us. We have lots of benchmarks that you can do and CLI commands for running locally. In terms of a established service like Sagemaker, we don't quite have the nice. We're not included with the package like Hugging Face is, so we have to make our own integration. But we've wrapped it up and added some ease of use that you can go ahead and get started with something like this and start experimenting the types of things you would like to build with on AWS.
All right. Well, any parting words for us, Michael? Where can I get started? You pointed us to the GitHub earlier. Is there anything that you'd like our audience to know to go sign up for, or any sort of trial, or just go for the open source version? What do you recommend?
Yeah. So I would say start off first by going to neuralmagic.com, learning about all that we do, how you can try it now on your local hardware or on an AWS instance. And just interact with the open source community, join our Slack, open an issue on GitHub. And we're really excited to be offering a new Neural Magic Labs opportunity that exposes sort of our ML experts and deployment optimized systems engineers that can guide you through your process of getting you to an optimized model and then making sure you're getting the most money out of your deployment. So we're really excited to be offering this sort of consultant offering and helping people make more optimized models, save money, and save the environment too, hopefully.
Yeah, I love that. Michael, Jillian, thank you both for joining. And please stay tuned for more content from AWS On Air. We'll be right back.